So our next part of the presentation, our next invited speaker. So Dr. Manav Saxena is with us today. So before proceeding with his talk, let me just introduce Dr. Manav Saxena. Dr. Manav Saxena obtained his PhD in chemistry from IIT Kanpur on carbon-based fluorescent material for bioimaging. In 2013, he was awarded UGC Dr. D.S. Kothari postdoctoral fellowship and joined IIEST Shibpur, Howrah. In 2014, he joined under Professor Rodney S. Roff, the CVD, who was the pioneer in CVD synthesis of graphene, as a postdoctoral fellow and achieved the first experimental evidence to convert bilayer graphene to single-layered diamond. In 2017, Dr. Saxena joined at the Center for Nano and Material Sciences, Jain, deemed to University, Bengaluru, as an assistant professor. Currently, he is serving as an associate professor in the department. He has published over 74 Q1 rank research articles, including Nature Nanotechnology, Journal of American Chemical Society, Journal of Materials Chemistry A, and ACS Applied Nanomaterials and Materials Today Chemistry. Under the SIRE program by DST India, Dr. Saxena visited Professor Yuri Gogotsky's research group, who was the MXZine inventor. For 6 months, he was at Drexel University, Philadelphia, USA. Currently, he is guiding 4 PhD scholars and several master's students. His research group is working on advanced low-dimensional materials for energy storage and conversion materials. So I hope Dr. Saxena is able to hear me.
So yeah, I think
yeah,
Dr. You can also hear me.
Yeah, right? You're audible, sir. So, sir, kindly proceed with your talk.
Okay, thank you for your kind introduction, and I'm thankful for the organizer to invite me for a talk. Wonderful. This is my second time I'm interacting with you people, and I'm very happy and excited to discuss here about our recent research which we have done here. So, as we know that all the research right nowadays is focusing mainly about the energy storage as well as energy conversion, because with the time lot of fuels, all the fuels and bio things, they are going to deplete, and people are need to take care of their environment also. So they want to do energy conversion or energy generation from renewable sources, as well as they want to store the energy material, whatever the energy is generating, excess energy, so they want to store it. So two areas, energy storage and energy conversion, is of high demand. So as you can see that a lot of research has been going on in the battery, fuel cell, supercapacitor, and based on the power density and energy density, the capacitor, fuel cell, and battery can be divided. And there are a lot of researches going on based on the electrode material, based on the electrolyte of the supercapacitor. So it different part, I can say even each single part of this energy storage and energy conversion material are a topic of a research. So people are working on material which shows either energy storage or energy conversion. There are only few research where people are doing a bifunctional material which can work as a energy storage as well as energy conversion also. So here we can see in the next slide here. So supercapacitor and battery, a very example which can be easily understand, that when we need immediate power, we need supercapacitor, and when we need power in a long run, we need battery type thing. And based upon the charge storage mechanism, the double layer charge storage mechanism, pseudo capacitive or battery type, these battery and supercapacitor have different type of charge storage mechanism, which has shown here as in a figure A, B, and C. Now, if we talk about the flexible materials, flexible materials, and we can see that a lot of people are working on the carbon cloth or the flexible type of materials for wearable and implantable energy devices, because nowadays this medical things where they can treat sense our sweat, our tears, and they can show the glucose meter and any type of uh, diseases if we are having or we are going to have in future. So there are a lot of electronics engineering is going on in wearable and implantable materials. So for that we need a ultra thin material, the bulk material. We have to make a film, and the problem is when you move the material flexible in plane and out plane, so there is a problem with the material, it can break. So if we can make a ultra thin material where thickness can reduce, so that will be a good thing, and also it can go for the fast ion transport. Here you can see there are a lot of method which is used to make this type of electrode and electrode material, like imprint module, layer by layer, mask method, inkjet or screen printing, or laser. So here in our research we are doing the laser, we are using this laser processing, and which we are going to explain in few slides. In common synthesis, if we see that people are a lot of research has been done on the autoclave hydrothermal synthesis, and we can obtain various type of morphology. But those morphology are particle based things. But making a ultra thin film, a flat thin on centimeter square using transition metal is really challenging, because transition metals are not natural layered materials in general. So breaking the crystal symmetry and making the anisotropy crystal growth is very critical in case of non-layered materials, and overcoming challenges such as random assembly, complex synthesis, poor interfacial contact is also a critical challenges which we have to develop if we want to work on the ultra thin materials. So here also, before going to experiment part, I can show that there are different type of history of structure where material A, B, C are grown in a lateral phase, whereas there are some other heterostructure where on like a sandwich type of structure, their layers are put on the top one by one, and we can make a very vertical heterostructures. Now, so these are vertical heterostructure also called van der Waals heterostructures, and they have different type of exciting property where we can tune the band gap, we can tune the optical transparency, because if material is ultra thin, it is transparent almost 99% to the optical light in the visual region. Now, if you put one layer, two layer, three layer, so you can tune the optical transparency. So here we have come up with a method where we are going to use a amphiphilic molecules, and we want a metal ion solution, and there we can just reduce it, and not reduce, we can make some reaction where we can make a where we can reduce only the metal ion present on solution and air interface. So we are not reducing the complete metal ion which is in the solution. We are reducing only the metal ion which are interacting with the amphiphilic molecules at solvent and air interface, and we can get this type of metal hydroxide layer which we can scoop on anywhere. So the thing is, can we do this type of research? So that is a question we asked, and this is the hypothesis, and we asked with ourselves, and then we made it. Now if we see the cobalt based material, so we started the cobalt ions and we treated with the HMTA, hexamethyl tetraamine, and the thing is, it is at 60 degrees centigrade, this HMTA, it dissociates into the ammonia and formaldehyde. Ammonia in presence of water, and it gives hydroxide ion and a basic medium. And as SDS is on the top layer, so the cobalt ion interacting with the SDS and the hydroxide generated from HMTA, it interacted with the cobalt ion and make cobalt hydroxide. So we can make a film of the size of the complete Petri plate, cobalt hydroxide film, which we can scoop on any substrate, whether you have a silicon wafer, you have a platinum, you have a gold, any substrate where you want, you can transfer it. And here in figure B, you can see the optical images where the film is a complete area, only you can see the minor cracks, where only you can see the difference. Figure C, the SEM image, you can see the wrinkles due to the transfer process. So wrinkles also suggest that images, the film is flexible. And also based on the AFM, we can show that the thickness of the sheet is around 4.3 nanometer, and which is quite thin, and it has a large area. So this has a very beneficial over the hydrothermal synthesis all, where we cannot achieve a large area, even millimeter square. So we are achieving the centimeter square things. And it can show the OER application in the basic media, and it is even at par as per the standard OER catalyst, which is ruthenium oxide in the basic media. We have done all the complete study, and we have also made the device where we have done the current collector, and which is it is a symmetry device, and we have used the separator and electrolyte, and we made a device, and it is stable up to 10,000 charge discharge cycle. And because the material is around 4 nanometer thin, so it is a flexible device also. And we have done all the catalyst study, and we have published it in Materials Today Energy before. Now when we are working on cobalt, is it possible with the nickel also? And this one work of this cobalt also we have published recently 2024 in JMC A, where we have done the flexible micro supercapacitor. So in the nickel based compound, we have also found the same technique, where we have done the aqueous solution pH 7, and we make a large area thin film, and we have published it in Journal of Colloidal and Interfaces. Now we have tried cobalt, we have tried nickel. Now the question comes for interesting: can we make a mixture of cobalt or nickel film, where somewhere cobalt region is there, nickel region is there, and there is a difference in little bit of the electronegativity, there is a difference of the one electron, and a study some exciting property can be seen for um, charge storage or OER application. If yes, then can we find the mechanism that how it is happening? So what we have done, we have taken a solution of cobalt and nickel ions, and with the same process we have made a sheet, and we have achieved the manually the thinnest sheet of around 3.6 nanometer. We have done it with the XRD and TM analysis. You can see that it is crystalline in nature. SAD pattern also shows that crystalline in nature, and TM also shows it's a uniform. And here we can see the elemental mapping, where cobalt, nickel, and oxygen are distributed over everywhere. Now we have done theoretical analysis that why this is happening, why this is shown, and we have used different composition of cobalt and nickel, molar ratios of cobalt, molar ratio of nickel, even equimolar ratios. So we have done all these things. Now figure H is the interesting one out of that. So figure H is about the in situ Raman. We are doing the charge analysis, charge storage. We are charging, we are discharging, and we are doing in situ Raman, and we can find the formation of cobalt and nickel oxyhydroxide. Means cobalt to nickel 2 is changing to +3 oxidation state, and upon discharging it is coming back. So at different potential we have done all the analysis, and we said we found the mechanism that how it is going in the ultra thin film, because for the bulk material it is well known, we can do even with the XRD, but for the thin film it is challenging. So recently we have published this one, and now the comes is vertical heterostructure or van der Waals heterostructures. And this is As per my best knowledge, this is the first study of transition metals vertical heterostructure of a large area. So what we have done, as I have shown in the previous slide, that we have made a film. Now we made a cobalt hydroxide film. We transfer nickel hydroxide film on that. In another set, we have done nickel hydroxide film. We scooped the nickel hydroxide film on the substrate, we dried it, and then we transferred on the cobalt hydroxide. So we make the two combination where on the substrate cobalt hydroxide and then nickel hydroxide on top. Another thing is where nickel hydroxide is on the substrate and cobalt hydroxide on the top. And we use this micro supercapacitor device as well as complete device. So here you can see that figure B, the nanosheet is there, and we have studied this vertical heterostructure by AFM analysis, and we can find the complete thickness of the film at the edge. We can see the sharp edges is around 6 nanometer, and we have done the XPS study where it shows that cobalt and nickel both are in +2 oxidation state, and there is some trapped water between the layers, because whatever we can dry, we cannot completely remove the water from the layer in between the substrate and the layer, and the in between the layer. So there is some amount of the water also present. Here we can see uh, the TM analysis in the figure A. We can see the large area, we can see the wrinkles, it shows the flexibility of the sheet and the crystalline size domain, crystalline domain, which is of around 2 nanometer crystalline domain. So there are a lot of domains which are present there. At present, all domains are not aligning in one direction. So it's a polycrystalline type of things. We are trying to achieve a film where all the domains are aligning in a particular direction. So we can get much more exciting properties. And based on the SAD pattern we have shown, which is and also the D spacing and elemental mapping G, H, and I, it shows the whole distribution of the cobalt, nickel, and here in the heterostructure. Here we are presenting the data of the where nickel on the top and cobalt on the substrate. So we have done the CV analysis at 100 millivolts per second, and we try to find that which electrode material shows a good performance for the charge storage. And we have found that when nickel is on the top in the vertical heterostructure or van der Waals heterostructure, it shows better performance as compared to when cobalt is there. So we were thinking that why it is happening. So we thought, okay, let's do some theoretical study, and we collaborated and we found this for heterostructure. So that there is a difference in the D states of cobalt in cobalt and nickel heterostructures, and there is an enhanced D state in the vertical heterostructures, and that is why the capacitance and capacity, the charge storage power of nickel and cobalt heterostructure is more as compared to the cobalt and nickel, where nickel is on bottom and cobalt on top. So we found this theoretical state help, and then we have done different rate. Um, we have done the CV at different scan rate, and we found that B value is close to 1, which shows a capacitive type of storage. But however, we can see uh, the material shows CV of the redox peak, which is a contradict things. In general, when we talk about bulk material. But here, our material is very thin, around total 6 nanometer or 3 nanometer or 2 point something nanometer for one film. So the electrolyte cannot pass between the material. It has to go only on the surface. And there are a lot of active site hydroxyl group on the surface, and it is a surface sensitive phenomenon. So that is why we are getting a capacitive type of charge storage mechanism, which we have shown here. And based on the GCD, we have calculated the volumetric capacity as well as the areal capacity of the material. So we have done the two electrode configuration, and we have done the cyclic stability. Cyclic stability even up to goes to 30,000 cycles. And just we have to keep in mind that understand that the material is only 2 or 3 nanometer thin. So the very ultra thin material is showing up to cyclic stability up to 30,000 charge and discharge cycle. And the first and last cycle is shown here for confirmation, and it can go up to 65% of the retention. So what happened after charge and discharge of 30,000 cycle? What is there any change? Because performance is decreasing. So means performance is decreasing. Definitely there is some changes in the oxidation state of the nickel or the cobalt, anything. So we have done the XPS before and after. So after the device fabrication, so we have opened it and we have done the XC2 XPS, and we have see that there is a formation of cobalt 3 as well as nickel 3, and that is now not reversible. It is like a stable kind of things, and it becomes a nickel 3, and that is why the performance of the device is decreasing after 30,000 cycle. So nickel 2 or cobalt 2 converted to the plus 3 oxidation state, and it is not coming back. Of some of the portion, we have found that how much we have done the quantification based on the XPS analysis, that how it is, and we have done also oxygen, we are lottious oxygen, and we can see the hydroxide also. And for the same material, we have fabricate a flexible device where we can see that up to 15,000 cycle, it is showing a good capacitance retention. And this device is quite transparent and flexible. We can made it this. And here you can see we have connected in the series and the parallel, as well as we have done the bending angle test. Because if you have a flexible device, then you have to bend it. Otherwise, there is no meaning of the flexible device. So we can bend it. So we have done the bending test at 0, 45 degree, 90 degree, and we can see based on the CV and GCD that there are very small changes in the charge storage performance, not that much, and the changes are less than approximately 8.5%. So that is not that big for a flexible device, and that is true when it is ultra thin in nature. So we have done all these analysis, and we found that this vertical heterostructures are giving much better performance as compared to their only single counterpart, only cobalt, only nickel. So that we have done. Why it is giving, we have done based on the theoretical study, and we found this, and this is probably the first time then, and we are going to submit it soon. It's not published yet, and these are acknowledgement for my funding agency, ANRF, DST, and Reliance, SERB previously, and all the my collaborator from the France who have done our help in the study, and thanks to my group. And this work has been done by Pallavi Jagdale and Saili Patel, those who are going to submit the thesis soon. So they have done all this analysis, and I'm really once again thankful for the convener to invite me and give me a chance for this wonderful conference. And I really previously I enjoyed the Wiley talk, and thank you. Thank you, sir.
Thank you, sir, Dr. Saxena, for such a beautiful talk on energy storage materials. So I request the participants, if they have queries, kindly come up with your queries. So you can write in the chat box also. So any participant? Okay, sir, I'll ask some doubts here, queries only. So if you can go to the PPT which you showed for nickel, cobalt nickel, that cobalt nickel system, can you just?
This vertical heterostructure or alloy one? Sorry,
That
this one or?
After that, sir, after that, here that analytical curves, charge discharge curves is shown there, sir.
Yes,
Yes, I
one is
have this
this.
three electrode system, and next was two electrode system. So just my query is this charge discharge behavior. Uh, Generally, it will be V-shaped, right? Means if we
Yes,
say for ideal behavior. So here I find some plateau regions. If we
yes.
notice. So can you just explain? And the two electrode system, there is a different feature. So
So, yeah, thank you. And it's really nice. And we also thought when we are doing this work, first this question comes. Actually, the V shape is complete comes when it is completely a capacitive material. Now it is nickel. Nickel shows the battery type of behavior, but when it is in bulk, it completely show the diffusive type of mechanism. If I see here, this figure M, it is a bulk material. Then this red part will be more, and this kind of green or part will be very less. But there, when we go with in an ultra thin film, then what happened? It's a surface sensitive phenomenon. But surface sensitive phenomena, so the capacitive nature is more, and the diffusive is less. But here the Plato reason is just because of the nickel has a tendency of the redox behavior. So that is why this is a Plato. And that is why, because of the Plato reason, we have not calculated the capacitance. So we have calculated here you can see in the figure O, the capacity, because it's not correct, scientifically correct to explain or calculate the capacitance when our plate GCD shows the Plato. It's not the V shape as you said, sir. And that's completely correct. And also CV has a strong redox peak. So that's why we have done the capacity calculation, like for the battery. But the charge storage mechanism is the capacitive type. And when we go for the two electrode system, in that sense, what happened? Then it is a complete cell. So in that, the charge discharge and curve and the symmetric cell. This is a symmetric cell. If we take this data in the asymmetric, the result will be different. So in the symmetric cell, always this the charge storage and all, it comes almost a complete behavior of the capacitance type. However, still we can see this redox peak here, a strong redox peak around 0.58 or something. So that is the thing. So that is why we can calculated the capacitance, whereas here we have calculated the only the capacity, the volumetric and well as areal capacity.
yes, sir, thank you. I got it. So because of the thin film behavior of the
Yes, sir.
nickel. Okay. So this flexible capacitor means, did you make a device out of it? Because
Yes, sir. We
or
have
it is
make
in
a
physical state. Okay, so go on.
no, no. We have make this. All you can see here, figure A. We have make a device. So this is connection of the three device. We make the single device also. Here in figure I, you can see. Wait a minute. Here you can see the one device, and we have also tested the series connection as well as the parallel connection, so we can get more current and more this. So we have this laser machine with our collaborator, and we have done this stage. So this laser machine, what we say, so we have the substrate, we mask it, and we use this high power laser, and this substrate turned to the a not graphene but graphene type of carbon, so it is highly conductive, so it works as an electrode, and we transfer our material to this electrode material, which we can see here in figure A and figure B, like series and parallel. So this is our actual device, and then we pack it. So it's a complete device we have made, and this testing of the bending angle flexibility we have done in the complete device set.
Yes, sir. Thank you. Thank you. So there are no more questions, I think, from participants. So once again, we thank Dr. Manav Saxena for his such an invigorating lecture on these energy storage materials. So, sir, wishes from us from MITS.
Thank you, sir.
Second time you.
Thank you.
Yeah, we are very happy to have you. Yes, so thank you, sir.